Okay, so here we are, and we're thinking about the period of Mars. How long does it take Mars to go around the sun? And one trip. So the period of Mars is what we're looking for. Our formula that was all reduced and simplified was G, the mass of the thing in the center. In this case, the thing in the center is the sun, equals the radius of the travel of Mars times the velocity squared. And so that's the basic equation, but I'm looking for period, and period is time, and I don't see that in any of these. So I'm going to have to go somewhere else to answer this equation. Answer this question. So the equation I'll pull out is period is distance divided by velocity. So the distance that Mars goes in its travels is going to be the distance around the circle, 2 pi r, the circumference. R is known, and in this problem it was 2.3. It was given. We used it in the last problem, 2.3 times 10 to the 11th meters. And we're going to divide by the velocity, which is what we actually calculated on the last problem. And Mars's velocity was 2.4 times 10 to the 4th meters per second. So when I tippy tap that, divide it by that, I get 6.0 times 10 to the 7th second. So is that longer than our year? Is Mars' year longer than our year? We'll take that number, divide it by 60, then it'll be in minutes. Divide it in 60, then it'll be in hours. Divide it by 24, then it'll be in days. And then divide it by 365, and it'll be in years. So I think it comes out close to 2 years. Maybe, was it 1? So this is in seconds, so it's about 1.9 years? Or 2 years, something like that. So Mars is further from the sun than Earth, so it's a longer path around the sun. So it makes sense that it would have a longer year if it's not going a whole lot faster than the Earth is. All right, the last example I'm going to give you is simply find the mass of the sun. We actually used the mass of the sun in one problem, but let's say we don't know it this time, and we're going to find the mass of the sun. Everyone should know the mass of the sun. So I know that boiled down equation was gravity, mass of the thing in the center, equals radius times velocity squared. So this time I'm going to head down this equation because mass of the thing in the center, says that my time's up, but I don't think it is. I don't think I've talked for 12 minutes. So I'm going to keep going. I can split the video up if it's too long. So this is the mass of the sun in this problem. So we have G, 6.67 times 10 to the negative 11 times the mass of the sun is what we're looking for, equals, we need some planet to help us with that. There's got to be something revolving around something. So let's put the sun in the middle, and let's use planet Earth. We have lots of data about planet Earth. So when we get to radius, the radius of the Earth's travels around the sun, that would be known. So I would have given you that before you do this problem. And then we get velocity, and the velocity of the Earth is not known. So where do we go? So we can't really do this problem because it has two unknowns. So I think I can go find this somewhere else. So where can I go to find that out? Well, I know that velocity, up here I saw time is velocity, distance over velocity. So I can rearrange that and say velocity is distance divided by time. But maybe I can get it out of this and then go back here and finish finding the mass of the sun. Sound like a plan? All right, so how far is it when the Earth goes around the sun? Well, I don't know. So I have 2 pi r. Do I know the radius? I do, because I used it right here. So do I know the time that it takes the Earth to go around? It's a year. So I can find that in seconds. So I have velocity is 2 pi. When I get to r, I'm going to grab the radius of the Earth's trip around the sun, 1.51 times 10 to the 11th. And I'm going to divide that by time. It takes the Earth 3.2 times 10 to the 7th seconds to go around the sun. So I would have given you that. Or you could have calculated it from the fact that 1 year is that many seconds. But I gave it to you. When I tippy tap that out, I get 3.0 times 10 to the 4th, 10 to the 4th. So 3.0 times 10 to the 4th is the velocity of the Earth as it travels around the sun. So I can go back here and plug that in here where it is sorely, sorely needed. So I'll put in that, and it's again, where'd it go? 3.0 times 10 to the 4th. And remember, in that equation, it's squared. So I'll move this to this side of the equation by division, 6.67 times 10 to the minus 11. So now, to find the mass of the sun, I plug in 1.51 times 10 to the negative, that wasn't negative, was it? That one was, I can't read my own writing, 1.51 times 10 to the 11th. I have a little doot there, but I think it was just from something that didn't get erased totally. It wouldn't be negative 11. So, yeah, mass of the sun equals 1.51 times 10 to the 11th times 3.0 times 10 to the 4th quantity squared over 6.67 times 10 to the minus 11. So when you tap all that out, the mass of the sun comes out to be 2.0 times 10 to the 30. And that's a mass, so it's in kilograms. All right. So hopefully you get to see how to use this equation and this equation, and sometimes both at once. So let's see how you do. Well, I think that's all I'll do right now. When you come in on Tuesday, we'll go over these examples again, and I will give you a worksheet, and it'll have 4 big mamas on it, 4 big problems for you to try. And so I'd like you to watch this video and jot down the information. It won't hurt to watch it again, and come in prepared to put these formulas into action and follow your mathematical nose. You have a good rest of the snow break, and I will see you when I see you. Till then, bye.